It's time for our next feat in magnetism. And that is the Biot-Savart relationship. These are French people, so it's Biot-Savart. I don't know why French words have so many extra useless consonants at the end, but did you ever notice that? Like, you can always get rid of just like the last couple letters in the French language, and it always sounds the same, right? But there are enough things wrong with English where I'm not going to really pick on that anymore. Okay. Now, remember I made that chart in electrostatics where you say, oh, I have charge and I want the E field. I need Coulomb's law. Oh, I have charge, I want voltage. I need that voltage integral law. Well, in this, the Biot-Savart relationship allows us to say, okay, I have a current distribution and I want the magnetic field. I want the electrical engineering magnetic field, H vector. So the way we do this, and here's one of the reasons why electrical engineers like the Biot-Savart relationship, because it bears striking resemblance to Coulomb's law. Except instead of little charges, we have little current elements. Let me show you what I mean here. So here, at this point here, I have a current element. So that means there's a little vector. It is length dl vector. That means dl is like an incremental length, vanishingly small, and it points in a specific direction. And the current amplitude on that is I. So you think of it as like a little piece of wire in space. It has a direction and it has an amplitude. And it also has a length, but it's an incremental length. Because what we're really trying to make in this analogy to help set up our integrals is we're going to basically use this and call this our point charge. So you have a little current increment. That's the equivalent of a point charge in electrostatics. And then, some ways away, call it r units away, we have a point of observation. And in some direction there will be an H field at that point of observation R. We will call the vector position of this thing R prime, which will eventually turn into our variable of integration as we look at a more difficult problem. So let's see. I should probably be consistent here. Let's see. If I've got this, it's kind of going into the board. Let's pretend this is going into the board. And by the right-hand rule, we know that the H field is probably going to point down at that point of observation. In fact, the actual mathematical relationship that we would write here is dH, the incremental change in the magnetic field, is equal to I dl crossed into a unit vector, call it r hat, that points in the direction of the point of observation. Then we divide by 4 pi r squared. And so we see there's a striking resemblance to what we've already studied in electrostatics. Here's something like a point charge. You're crossing it into this unit vector to resolve sort of the direction of the force where this H field is pointing. Oh, and it falls off 1 over r squared, 4 pi r squared. So double the distance, quadruple the loss in terms of the amplitude of the magnetic field. Now, the only thing that's kind of different, that's a little quirky, besides the fact that we've got that cross product, is that we have these D differential elements here. You'll rarely see, you won't ever see the d's removed in the expression given as anything other than partial with respect to h, because physicists and electrical engineers alike do like to be consistent with the math. And technically, you cannot have a little current element isolated in space. Because what does that mean? That means that charges are depleting here, so this area in space is becoming more and more negative with respect to time, and charges are increasing over here. Positive charges are being deposited there, because if there's no other current in space, it's got to be building up at that point. And therefore, this is highly misleading if it's not described as just a partial element of H. What it really is going to be is part of a loop of current, right? The current always has to come back in on itself, a la Kirchhoff's current law. And so we recognize that we're going to have to even though this is kind of like a point charge formula that we use for convenience to parallel Coulomb's law, there's going to have to be some pathway that we integrate around. There's no such thing as a hunk of disembodied magnetostatic current. There is such a thing as a point charge, though. So we don't do that for Coulomb's law. So you can call this a point current relationship, so to speak. Now, in integral form, if we want more usable forms of this law that do actually have loops that finish in on themselves, let's look at the following integral forms of Biot-Savart. Well, if we want to integrate around a path, we can do I dl, where dl is that incremental path element of integration around whatever contour that we've picked. We cross that into the unit vector r hat, and we divide by 4 pi r squared. And in this case, we are going hopefully around a closed path. Eventually around a closed path. In fact, you'll often see this integral expressed, I think your book does this, well, they'll actually just emphasize, oh, this is a closed path integral. So I'm going to put a circle around it to denote that the stopping point is the same as the starting point. Now let me massage this so that it's a little bit more familiar. R, of course, is the distance between my point of observation and my variable of integration. In fact, let's go ahead and put a little dot there just to denote that we are now integrating. And this is where my variable of integration is. It's pointing all along here. And there's some variable of integration wrapped up in this quantity and this quantity as well, as I slide around and pick up all the contributions of the current elements when I'm building my H field in a certain point of observation. The R, here's the dependence. This is my point of observation R. My variable of integration is my r prime that's sliding around the loop. And r hat is the unit vector that points from wherever I'm integrating at the loop to my point of observation. So I can write that as r minus r prime, because that gives me the direction, and then I normalize it. To get a true unit vector. So if that's the case, then look what this becomes. I'm going around a path. Yeah, I'll put the circle in just for grins. This is going to be I dl prime crossed into, I've got this vector here, r minus r prime, and it's divided by 4 pi. I've got magnitude squared in the denominator, and remember, I got to have another magnitude squared to normalize the effect of this vector. Where have we seen that before? This looks just like Coulomb's law, except now instead of q times r minus r prime times a differential element, I've got to do a cross product of my path element into that vector instead. Now, just for completeness, to make sure that we have everything that we need to solve these problems in the notes, we've never actually put the definition of a cross product up. That shouldn't be a problem. I think all of you have seen that in at least 1 or 2 other classes, right? But just for grins, let's write the definition up on the board, because it might have been a few semesters. A crossed into B. Well, there's a couple different ways to compute this. The one I always like the most is that determinant method, where you take a 3 by 3 matrix. You put x hat, y hat, z hat on the first row. You put ax, ay, az, the x, y, z components of your first vector on the second row, and bx, by, bz, the x, y, z components of the element in your second row, your second element. And then you just do a determinant, which of course is a couple different ways to compute a determinant, right? You can do diagonal, 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 minus diagonal, diagonal, diagonal. Or you could do that subdeterminant method, which basically says, okay, cover up this row and this column. The subdeterminant of this guy is going to get stuck on the x hat component. Then I move to the center, flip the sign, and do the same subdeterminant, put it there. And move over here, do the same subdeterminant, put it over there. Let me write out that method, just because it's nice to have the algebraic full expression in your notes. Let's see. Subdeterminant, that's going to be ay, bz, this minus by, az, stick it on the x hat, plus, let's say I got y hat, ax, bz, and actually, because I'm in that center row, I got to flip the sign. So let me put a minus ax, bz, plus bx, az. And then I got to do the last one. ax, by, minus bx, ay. So that's how you would compute it if you're just given 2 generic vectors. And of course, it's not just important in this class, as you know, to simply just compute something. Not only do you have to compute it, but you have to figure out what does it actually mean. So what does a cross product actually mean? I always like the sort of geometrical meaning of a cross product more than anything. Well, it depends. If you have 2 vectors that are orthogonal to one another, or even if they're not orthogonal to one another, cross product will always be mutually perpendicular to those. That's right. So that tells us about the direction. Perfect. So if we had, say, A, and this is B, there are actually 2 vectors that could be perpendicular to both A and B simultaneously. It could point up, or it could point down. That's right. And how do you resolve which one? You whip up that right-hand rule again. The first thing, which is the A, crossed into the second thing, which is the B, should give you A cross B. Now, interestingly enough, if you switch the order, if you do B crossed into A, you'll get the opposite sign. It's always something that bites students in some computations, the fact that the cross product is not reciprocal. Cross product is not reciprocal. So that tells us about the direction, where it's going to point. What about the magnitude? What does the magnitude of a cross product mean? Yeah, kind of. So the projection, dot product is more of a projection, but if you kind of view A and B as forming a parallelogram, then the area in here is actually the magnitude of the cross product. So in that way, it's kind of opposite the dot product. This value is maximized when the two vectors are orthogonal to one another. Because, of course, if this is a square like this, this has the most area. So at 90 degrees, the magnitude of the cross product is maximized. When they're almost collinear, they have very little area in their parallelogram, and you get a very small value. You get 0 whenever A and B are truly collinear. 0, and then the direction is irrelevant, right? Which direction does the 0 vector point? I don't know. Can't normalize it. So anyway, just a little bit of a review of cross products. Okay, so back to our integral here. We now have everything that we need to know to do with a path integral. You see that it could be kind of tedious depending on the geometry. Although, as I'll show you on some sample problems, if you're clever about how you pick your coordinate system and set the problem up, a lot of times this cross product in these magnetism problems are trivial to work out. You can use a little right-hand rule and figure out that, oh, it always points in the phi hat direction, or something like that. And then, of course, we know how to deal with all this other stuff as well, based on our ample practice with voltage and field integrals. Okay, so just a few alternative forms. We said last time that there were other ways to express currents, just as there were many different ways to express charges. So if instead of a line current, you are given a sheet of current, what we call a surface density, surface current density. So we usually give that for unknown reasons, reasons I cannot find, the variable K. That's just sort of the tradition. That has units of amps per meter. And if you were to draw it, it would look kind of like this. You'd have maybe a sheet of metal or some sort of conducting quantity, and there would be current that is confined to a plate. It's not a line current in the sense that it's all concentrated at one linear path in space, but it's also not a volume current in the sense that you have squeezed one dimension out of the path so that it's perfectly flat. Now keep in mind that depending on the shape of this metal and how things are oriented, that K could actually be a function of position. You know, the current could be denser and stronger in the middle of this as opposed to the end of it. In fact, that's actually how you make a Hall sensor. Anybody ever used one of those in your circuits lab or in your hobby days? Anybody know what that is? Hall sensor? Anybody know what the Hall effect is? Anybody know how to spell Hall? H-A-L-L. It's regular. It's regular. No, you're right. It can be used in a current sensor in conjunction with some other things. The Hall effect sensor is basically if you put a magnetic field on certain thin pieces of metal. What does a magnetic field do, right? If it's perpendicular to this conducting sheet, say you wire this up. And according to our Ohm's law analysis, this should be a nice uniform current being carried in the absence of magnetic field. But if you do impress a decent-sized magnetic field here, those charges well, they're electrons, right? So if they're traveling this way, the polarity is actually this way when you go to calculate that v vector. Charge times velocity is pointing this way. Crossed with the field, there's always a force pushing them to the right. If the B flips, then it's always a force pushing them to the left. And the Hall effect is some guy named Hall that basically found out that for these sheets of metal, the K, the current density, gets pushed to one side, kind of an exponential looking decay, and that exponent becomes steeper and steeper depending on the strength of the magnetic field. And if this is a very thin piece of metal with a known conductivity, then what that means is you're actually constricting the path of that current. And so by measuring the resistance of the ends of these 2 points, you are equivalently measuring the magnetic field. It's an inferred magnetic field measurement. So you just put this up to some ohm meter circuitry and make that measurement that way. You can buy these for really cheap off of probably, like, I don't know, what are those hobby electronic sites? I won't give them any free advertising, but you know the ones. A couple bucks and you can plop that in your circuit. Now, yeah, so that's, and so what they are often used for is in conjunction with a current transformer ring, which is an iron thing that you clamp around a wire. You can get a pretty good estimate of what the current is going through a wire, whatever that is going there. That has to do with Ampere's law. We haven't gotten to that yet. So good anticipation of the thing that we're going to cover. So anyway, this is a current law, a current density formula. And this is a little bit slight modification. If we want to find a magnetic field due to a current distribution at an arbitrary point in space, then the integral that we would use for that is a surface integral. We would take k, which is a function of my point of observation. And most of the problems that we're going to work, if we ever see a k, it's probably going to be a constant uniform current density vector, but just recognize that there are situations where non-constant ones exist, and that's very useful. That's going to cross into r minus r prime. I'm going to need to integrate with respect to that surface, and I've got 4 pi magnitude r minus r prime cubed. Oh yeah, Randy.
If k isn't constant, then how do you integrate that into the integral? Because then it'd be changing with...
Yeah, it is. Well, it's not changing with time, but it's changing with respect to space. So if you think about this kind of graphically, what this integral is doing is saying, it's using the little Biot-Savart formula that we originally came up and say, okay, I've got a little chunk of current there, that's going to contribute to there. I got a little chunk there, a little chunk there, and it just slides around as you integrate across the surface, picking up all the individual contributions. So if k is varying, then just think of that as an additional weighting to the contribution. If I'm over here where the k is bigger, then that's going to contribute more relative to the same amount of distance. So, but your intuition is right. These problems get to be kind of a bear if k is also varying with respect to the variable of integration. It's not just a nice little constant times a direction vector. The constant you could peel out, the direction vector, you could just calculate a priori what that cross product is. If this is actually wiggling around in both direction and amplitude, it becomes a much more complicated problem. You will likely not have to solve something like that for this class. But I put the general form on there just so you have it at your fingertips, if in the future you try to do that. Now, of course, that's a surface current density. We also know that there's a volume current density, our old friend J. Oops. J, which has units of amps per meter squared. Of course, that's we recognize that as being some sort of volume, V. And in there, we've got some current density flowing. It doesn't necessarily, again, have to be a constant. The direction and the amplitude could be changing within that volume such that the final expression, the full generic expression, is integration over that volume of j as a function of r primed crossed into r minus r prime dv prime divided by 4 pi r minus r prime to the cubed power. Yeah, sure.
Did they discover the volume current density or the surface current density first?
Did they discover it? That's a tough question. You know, I think there was this intuition that current existed, or maybe it would be better to say that they discovered current, and then these are kind of like three mathematical abstractions of current that follow pretty straightforward from that first discovery of current. So the idea is that, well, we know that there's something called charge, and when it starts moving, that's what we call current. And really, it's how do we mathematically describe that? And I think pretty readily these jump out as soon as you make that inference. So I'm not sure if anybody's actually discovered, if you could say anybody discovered, because technically, at the end of the day, it's all really just volume current, right? If you squeeze it into a really thin area, then you can treat it like a surface current. But it's never exactly zero, because atoms aren't zero in width. And likewise, there's no such thing as a zero diameter wire where you've taken all of your moving charges and put them into one point in space. But those are convenient levels of abstraction once you have the concept of current density flowing through a material. In fact, any of these other integrals, the line current or the sheet current, we could actually use this to solve all of them if we're like plugging in like delta functions in there to restrict one of the dimensions of my volume current. Make this k vector times some sort of delta function in one dimension. Okay. Well, enough of these abstract integrals. Let's actually solve a useful problem. Is one of the fundamental results in all of electromagnetism. Let's look at a magnetic field due to a loop current. Find H field at the center, which we'll call the origin in this problem, of a counterclockwise loop carrying current I at a radius r, comma, lying in the xy plane centered at the origin. So let me sketch that. Let's always start these problems by sketching. Here is our origin. It's at 0, 0, 0, and that's actually where we're going to observe our H field. We're going to have, in the xy plane, let me just draw my x and my y axes. In the xy plane, at a radius of capital R, a constant, I have a counterclockwise loop. So let's see, what is a counterclockwise loop? This is a clock, and I'm looking down. Clockwise is this way, counterclockwise is this way. And so this is a line current integral. And so I automatically know that h is going to be the integral I dl crossed into r minus r prime over 4 pi magnitude r minus r prime, quantity cubed. And this is going to be around a closed path, so if I want, I can put a circle there. No big deal if you don't. Okay, now I have to come up with some things to put in there. I should do it in a way that simplifies things. So right off the bat, you could probably guess I'm going to slip into the cylindrical coordinate system. Because otherwise, if you could work this in the Cartesian coordinate system, but you will be here for the next 2 days doing the mathematics. Instead, we're going to conveniently slip into the cylindrical coordinate system and describe points of observation that way and the unit vectors that way. And everything, especially the vectors, get handled very nicely. So let me go ahead and resolve this stuff. Okay, r, in this case, is 0, stick it on the x, 0, stick it on the y, 0, stick it on the z. R prime, I can write that in terms of my cylindrical coordinate system variables. Remember that rho times cosine of phi, stick it on the x, plus sine, rho sine cosine sine of phi, stick it on the y hat. And this is going to be 0 z hat, because that ring is in the xy plane. You're never increasing or decreasing in z. And this will describe my loop. In fact, I can even simplify things a little bit further. First of all, I note that my phi prime is my variable of integration. I'm going to be sliding around in phi. And I'm doing that at constant radius. My rho won't change. So in fact, I'm going to replace this rho with just a constant. Capital R, the radius of my circle. I don't need to let rho vary because I'm only going to be integrating a path in phi. Does that make sense? Everybody buy that so far? Yeah, so good? That's also, we got an r minus a r prime. So let's compute that really quick. If I subtract these two from one another, I got minus r cosine phi prime. Stick it on the x, minus r sine phi prime. Stick it on the y, and I don't have anything in z. Now my dl. This has got to have my element of integration. And remember, I'm going around a circle. If we look at that nice diagram that I always put up on the board, this is the one in your textbook in Chapter 1 when they talk about the cylindrical coordinate system. They've got something that resembles this. It has your volume elements of integration. And of course, we're just doing a single dimension, so we only have to pick out one of these. Which one do we pick out? This one, because we're going around a circle. And so that's going to be the amplitude of this vector, rho d phi prime. And of course, we're at a constant radius. So again, I can just make that capital R. I'm not integrating with respect to it, and it's being held constant in all the problem. So that's the amplitude. And which direction is this pointing? Let's see, if we're going counterclockwise, it's always pointing in the phi hat direction. Remember? Rho, phi hat, z. And as I spin around, my phi hat always points in the direction of tangential to the circle that I'm spinning around. So let me put this up here. Phi hat. Now we can kind of approach this two ways. Let's do it the long way just to make sure that we're consistent. I have a dl vector here, and I've got my r minus r prime vector here, I got to cross them in the denominator. Or in the numerator of that integral. So how do I do a cross product? X, Y, and Z. I put my first thing here. It's in the phi hat direction. Well, let's see. What does the phi hat direction look like? Phi hat, if I expand this out into Cartesian coordinates, I can write this as minus r sine phi d phi in the x direction plus r cosine phi d phi in the y hat direction. So let me go ahead and put those down. Minus r sine phi prime d phi prime plus r cosine phi prime d phi prime. Nothing on the z. Over here, for this last element, I already wrote that down. That's minus r cosine phi prime. This is minus r sine phi prime. Nothing on the z. So when I go to take the determinant of this thing, what I get...
Professor?
Yes?
I got a little lost up there. How do you go from r d phi prime phi hat to that second?
Oh, okay. Yeah, I'm sorry. I probably skipped this step that wasn't apparent there. So if you look in your book, phi prime is equal to minus sine phi prime on the x plus cosine phi prime. No, this is something I should not have skipped over here. So it's just how to express this vector, this unit vector, in terms of the Cartesian unit vectors. Yeah. Yeah, there's a table. I remember there was a cross product technique I showed you. You could always convert from one unit vector to any other unit vector by looking at that table and looking at the dot products. What is phi hat dotted into x hat? It's this. What is phi hat dotted into y hat? It's this. That gives you, that way you don't have to memorize 17 different formulas for all the coordinate systems. So sorry about that. So yeah, then you just distribute the r and the d phi prime. So now, going back over here, my subdeterminant of x, well, it has zeros. So I take this subdeterminant, that's going to be 0. I stick it on the x. When I take this subdeterminant with respect to y, that's also going to be 0. Stick it on the y. The only one that's not going to be 0 is this one. What I stick on the z is the subdeterminant of this little 2x2 matrix. So what does that give me? I've got r and an r. They're both minus, so I'm going to get a positive r squared. I get a sine phi prime squared, because I got a sine phi prime there and a sine phi prime there. And I get a d phi prime. Subtract out, what am I subtracting? A minus r times a positive r. Well, I'm subtracting a minus r squared, so that becomes positive r squared. I've got 2 cosines. So I'm going to square that, and I again have a d phi prime. Well, this is really nice. I got an r squared term that's common to both things in my summation. So I factor that out. Likewise, I can factor this out. And all I'm left with is sine squared plus cosine squared of phi. That's just 1, right? So all this work just to discover that r squared times d phi prime, and that's of course on the z hat unit vector, is my final answer. So that's good. The other thing that we're going to need, the last thing to finish out that integral, what's the magnitude of this? Well, remember, the point of observation is always at the center, and your variable of integration is sliding around a circle that's always r units away from the interior of that point. So this is always going to be the constant r. I don't even have to compute it. But if I wanted to, I could take the magnitude, the x component squared plus the y component squared, take the square root, and you see I get the same thing. So all of this setup just to show that that integral that we put up over there is actually pretty easy. Let's go ahead and take a look at it. We can tackle it now. I is a constant. I'm going to bring it out. Let's see. This cross product we've already evaluated to be r squared d phi prime z hat. We're actually integrating with respect to d phi prime. We're going from 0 to 2 pi. This other stuff is just a constant. I can take this out. R squared z prime. I'm dividing by 4 pi. Hey, that's another constant. And this evaluated to magnitude r cubed, this distance between the point of observation and my variable of integration. Hey, that's another constant. So at the end of the day, I'm just kind of chock full of constants. This is going to come out into the denominator, cancel 2 of those. And what I'm left with is just an integral from 0 to 2 pi. That's just going to be 2 pi. That's going to cancel with some of the 4 pi. At the end of the day, all I've got is I over 2r in the z hat direction. Does that make sense? Yeah, I think so. We know by the right-hand rule that all these contributions, as viewed from the center, are going to be adding up in the z hat direction by the right-hand rule. If I increase the current, that magnetic field increases in amplitude. It always points in z, but it gets bigger and bigger. And finally, if I increase the radius, if I stretch the radius out and hold the current constant, the total magnetic field drops because those elemental currents are acting at a farther distance. Yeah, Cameron.
I'm confused how you have the radius cubed in the denominator.
Oh, okay. So the radius cubed, we took this part of the denominator, we moved that out. This, what's left, is just the distance between the point of observation, which is at the origin, and the variable of integration, which is sliding around the circle, but is always a radius r away from the origin. So we could do that just geometrically. We say, well, we're always a constant r away from that. So that'd be r cubed. Or we could go over here, and we actually computed what that difference is, and we can say, well, the magnitude of this, of course, is r. R squared cosine squared plus r squared sine squared is r squared. Yeah. Oh, sorry. The guy behind you had his hand up first. We'll do it in order.
Could you go back over how you found DL again when you drew out the little cheese shape thing?
Yeah, sure. So in the first chapter of your book, they have these helpful diagrams. You've seen me draw these on the board before. So if you want to integrate in the volume of cylindrical coordinates, you got to use all these elements: d rho, dz, rho d phi. Conveniently, in this diagram, they've got the portions of the elements that line up in the direction of integration, such that if you want to integrate across, say, a surface, for example, a disk, well, a disk, you're going to take basically this surface element and slide it around in phi and rho. And so in doing so, you got to use this element times this element in your variable in your integration. Now, in this case, we're doing a path integral, so we only need one of these 3 dimensions. And it happens to line up with the circle. So let's kind of think of that as the arc here. And so that's the one we take. We're not changing position with respect to z. We're not integrating in and out with respect to rho. It's only around with respect to phi. So this is the one that we pick off. And this is a helpful diagram because a lot of times, especially when you're first approaching these problems, you drop the rho by accident. You think, oh, I'm just integrating with respect to phi. It's like, oh, no, wait a second. You can't do that. You're integrating with respect to a circular path. So the thing that you need to integrate with has to have units of meters, right? And this helps you. This little diagram helps you remember that when you're constructing these integrals. Randy, was that the same question?
Well, kind of, but I was going to say, what if I forget my trigonometric properties, like sine squared plus cosine squared is 1, and I just left it like that instead of reducing it down to the r squared d theta? I mean d.
I would throw this marker at you. Well, no, in the test, I would probably, when I handed your test back, I'd roll it up.
You probably write lazy like you did on my last paper.
Maybe that was the TA. I don't know. No, actually, the TA didn't grade any of your last paper. I always grade the tests to minimize controversy. So if you have a problem with your homework, go see the TA. If you have a problem with your test, come see me. I can't believe somebody must have broken into my office and wrote that on the test. Okay. Any more questions about this example? Okay.